Swayam Prabha. Digital India. Educated India.
Welcome once again to our discussion on natural resource economics. We were specifically discussing about the optimum extraction of a renewable resource, taking fishery as an example. And then what we discussed, if you recall in our last class, that we discussed a biological model and then we discussed an economist model. So, when there is no human being in the picture, that means we assumed a lake full of fish, but that is undiscovered by human being. So, when it is undiscovered and undisturbed by human beings, then it is a purely biological setup, and that is why we discussed about a biological growth model in the context of that fishery. And we said that in this biological setup, it is a stock dependent growth, right? It is a stock dependent growth. There are two important elements in that stock dependent growth model. Basically, the critical amount of species or critical amount of fish that is required for its regenerating capacity to be exhibited. We call it X mean, and then we said that the growth of this species has basically two roots. One is at the X mean and another also another point at Xc. Why two roots? Because in that growth path we have a maximum or optimum point in the growth path where growth rate is 0, and if the stock exceeds beyond that, we said that there would be much more competition among these species for food and oxygen, and that is why the stock will come down and again it will become 0. And then we derived the optimality condition, and if you recall at last, so basically this is what we are discussing is let us say optimum extraction of a renewable resource. So, the last condition, if you remember, we derived this condition rho dot t equals to rho dot t minus del c dot del xt plus rho t into del g dot del x t equals to r into rho t. And we said that this r into rho t is basically the total benefit for preserving the resource for tomorrow, and it has several components. The first component, we said that this rho dot t is basically the capital gain, then del c dot del x t, this is the stock effect on the cost of extraction, and then the third component is the benefit due to biological growth. And we said that at steady state, rho dot t equals to 0, and that implies at steady state rho dot t equals to 0. So, that means r into rho t plus del C dot del x t minus rho t into del g del x t equals to 0. Okay. And at steady state we also know that growth of extraction x dot t is also 0. So, this is let us say condition 1 at steady state, and x dot t equals to 0 implies that growth, stock dependent growth equals to rate of extraction. So, this is also these two, I will say that these are the two condition 1 and 2 that happens at steady state. Okay. Now, from these steady state condition, today we are going to introduce another concept which is called catch locus, Let us say that we will introduce catch locus with a simple diagram. Okay. Let us say that this is the revenue curve, R curve, revenue that you will generate by catching fish. And let us say that we have this is let us say cost curve, cost of extraction that depends on your rate of extraction and let us say your stock. Okay. So, from this curve what you can see that cost curve is a function of two things, cost of extraction and the rate of extraction and the stock. If you have more stock, then obviously cost would be less. If you have less stock, then cost would be more. Suppose keeping rate of extraction constant, stock of the resource, let us say this is x equals to x1, stock of the resource increases. So, what will happen when stock of the resource increases? So, obviously cost curve will come down. So, this is a cost corresponding to y, but x equals to x2, okay, where we assume that x2 is actually greater than x1. This is the assumption. And the difference between cost and the revenue is a profit, right, is a profit. Okay. So, actually we can actually draw different harvest cost function based on the stock. So, we can draw different harvest cost or cost of extraction. We call it harvest cost function. This is C is actually harvest cost function. You can say this is C1, this is C2, you can call it harvest cost function depending on stocks. Okay. So, C1 is the first harvest cost function, C2 is the second harvest cost function. Okay. Now, let us assume that along the optimum harvest path, okay, along the optimum harvest path, what we will get? PT price should be equals to rho t plus del C del YT. Okay. So, price equals to marginal cost plus this shadow price, okay. That is derived from the first order necessary condition, from first order necessary condition we derived earlier, that along the optimum path or harvest, price should be equals to cost of extraction plus this shadow price. Now, let us suppose at point M and N, let us say this is point M and this is point M. Suppose at points M and N, point M and N, the above condition is satisfied. That means this condition Pt equals to rho t plus del C dot del Yt is satisfied. The above condition is satisfied. Okay. So, what will happen? We will say that means what you can write is that this is optimum harvest corresponding to M and this is optimum harvest corresponding to Y. So, in this axis we are measuring harvest, rate of extraction, here we are measuring cost which is a function of Y and X. Okay. So, Y1 is basically the optimum harvest when X equals to X1, Y1 star is optimum harvest when X equals to X1, and Y2 is optimum harvest when X equals to X2. Okay. Now, if we join the points like M and N, okay, points like M and N where this optimality condition is satisfied, then we will have a locus like this. So, if we join point like M N, we will have point like this, okay, and that is called catch locus. So, that is called catch locus. So, this is catch locus. Okay. This is catch locus. So, what is catch locus then? What we have defined? See, first we have drawn the harvest cost function, then depending on different level of stock we will have different cost function, and then we assume along this harvest cost function there are points like M and N where this first order necessary condition is satisfied. M is the point on the first cost harvest function where this condition is satisfied, and N is the point where the FNC is satisfied. Now, Y1 star is basically giving the optimum harvest when stock equals to X1, Y2 is the optimum harvest when it is stock is X is X2. So, by joining this type of different optimum points, what we will get? We will get a catch locus. Okay, we will get a catch locus. So, catch locus is the locus which shows different level of catch, optimum harvest depending on the stock, So, these are all coming from connecting out the optimum harvest point, okay, optimum harvest point. Okay. So, what we will write here, by joining points like M and N, we can get a locus. By joining points like M, N, so on, what we will get? We get a locus, which shows different level of harvest, based on stock. Okay. So, this locus is called, catch locus. Okay. So, if we assume that harvest cost of harvest is low, or we can assume that fishes are highly valued, then what will happen? The revenue curve or the R curve will be very steep, because fishes are highly valued. That means the price of the fish is so good and cost of harvest is very low. So, the revenue that you generate out of this fishing, that would be too much revenue would be generated, and the revenue curve would be more steep, will be very steep, okay, very steep. And what will happen? That very steep, and since the cost of harvest is low, cost of harvest is also low. So, cost curve will shift downward, downward, and if the cost curve shifts downward, we can go back to the diagram. So, what we are assuming that cost of extraction is low because stock is increasing. So, this curve will shift downward, and as this cost curve shifts downwards, catch locus will shift upward, because you want to have more and more harvest. From the diagram also, if this curve again comes down, so this point will be shifting upwards.